High voltage direct current, HVDC, is often described as a key technology for the future of power systems. While its advantages are widely discussed, fewer videos explain both the strengths and the real challenges of HVDC in a balanced and practical way. This video does exactly that. It explains why HVDC is so powerful, but also why it is not used everywhere, using clear language and real engineering logic. HVDC is not a new invention, but recent advances in power electronics, control systems, and renewable energy integration have pushed it into the spotlight. Today, HVDC is no longer a niche solution. It is becoming a strategic infrastructure choice for modern power networks. One of the strongest advantages of HVDC is its ability to transmit power over very long distances with lower losses. Unlike a C transmission, there is no reactive power, no skin effect in the same way, and no charging current in cables. This makes HVDC especially efficient for long overhead lines, underground cables, and submarine cables. In many projects, HVDC becomes more economical than HVAC beyond a certain distance. HVDC systems allow operators to control power flow directly and instantly. This means exact control of transmitted power, fast response to disturbances, and improved system stability. In practice, HVDC links can act like controllable power valves, something a C lines cannot do. Renewable energy sources such as wind and solar are intermittent, often far from load centers and connected to weak grids. HVDC helps solve these problems by transmitting large amounts of power from remote areas, stabilizing weak networks, and connecting offshore wind farms to mainland grids. This is one reason why HVDC is central to the global energy transition. HVDC can connect power systems that operate at different frequencies, are not synchronized, or have different stability characteristics. This makes HVDC ideal for cross-border interconnections, island connections, and emergency support between grids. Such connections are impossible with conventional HVAC because HVDC decouples the sending and receiving systems. Disturbances do not propagate easily, oscillations are reduced, and blackout risks are lower. In modern grids with high renewable penetration, this stability advantage is extremely valuable. Despite its benefits, HVDC is not a perfect solution. Understanding its challenges is essential for realistic planning. HVDC converter stations are technically complex, equipment-intensive, and expensive to build. For short distances, the cost of converters can outweigh the efficiency benefits. This is why HVAC is still preferred for many projects. Protecting HVDC systems is more difficult than AC systems because DC faults rise very fast, there is no natural current zero crossing, and fault isolation must be extremely fast. DC circuit breakers and protection algorithms are still technically challenging, costly, and actively researched. This remains one of the biggest technical barriers, especially for multi-terminal HVDC systems. Modern HVDC systems rely heavily on digital control, communication networks, and coordinated algorithms. In multi-terminal HVDC grids, control interaction becomes complex, communication delays matter, and system-level coordination is critical. This requires advanced design and skilled operation. Compared to AC systems, HVDC still lacks unified global standards and fully interoperable equipment between vendors. This can increase project risk, reduce flexibility, and raise costs in large-scale deployments. Standardization is improving, but it is still evolving. The challenges of HVDC are engineering challenges, not fundamental limitations. With ongoing advances in power electronics, DC protection, control optimization, and communication technologies, many of today's limitations are being gradually overcome. For projects involving long distances, large power transfers, renewable energy integration, and grid interconnection, HVDC often remains the best available solution despite its complexity. HVDC should not be seen as a replacement for AC systems. Instead, FAFA forms the backbone of local grids, and HVDC strengthens long-distance and strategic links. The future grid will be a hybrid AC/DC system, combining the strengths of both AC and DC technologies. HVDC offers exceptional benefits in efficiency, controllability, and system stability, especially for modern energy challenges. At the same time, it introduces higher costs, technical complexity, and protection challenges. Understanding both sides of HVDC is essential, not only to appreciate its value, but also to design and operate it responsibly. To read the full article, visit my blog. The link is in the first pinned comment. Thanks for watching. Abdelazim said.